Hi, how's it going, guys? So, as you know, my last video was a few months ago, and I really wanted to shoot another video in the middle, but the thing is, my tripod broke down, and I had some things to be take care of, right? And I passed my third semester in data science and analytics from Central University, so that's a plus. Uh, Another thing is, I wanted to continue making videos, right? But I couldn't. But now I'm back. There were people coming up to me saying, "Where is a new video? We want a new video to learn, right?" And this is for students. This is for class 12 students, 10 students, even bachelor's degree students in other fields who want to learn something else, who want to expand their knowledge into data science because it's a developing field and it's been called the sexiest job of the century. So without further ado, let's start this course. So today I thought I would talk about statistical methods. Now statistical methods combines probability in data science, and it plays a very big role. Everything that we see from 1980, 1990 to around 2005 is completely based on pure statistics. So this pure statistics, it branched out into the fields of data science and used some machine learning algorithms that were being developed to create something new in data science. Before this, we had conceptual theories, like abstract theories from many mathematicians, like Alan Turing, for example, who thought that machine learning, deep learning, this should be done on the basis of actual human thinking. But the thing is, in 1990, it was found that computers are not that sufficient enough at that time to incorporate all these changes. So statistics was the next method. In 1997, I think. What came to be in that place was 15 years of pure mathematics, pure statistics, and every decision that the computer made, say for example decision trees, which I'll be talking later, was based on probability. Right? Much of what data science is, it's around 60% to 60% statistics and probability. So yeah, let's start this course. So it's called statistical methods, and here I'll be talking about the basic statistical distributions, what are the basic terminology, the different type of graphs and stuff like that, right? So let's begin. And if you are new to the channel, like and subscribe and hit that bell icon so that you'll get notifications in the future. So the first thing is data collection and visualization. So data collection, it is of two primary types, two main types, that is primary and secondary. So the primary, what primary data collection is you have to go out there and you do a survey of your own. You collect the data on your own. The researchers, this comes from research methodology, right? So the researcher, he will go out and do the survey on his own, and that is primary research. The secondary research or secondary data collection principle says that the data is already available in various journals, magazines, mathematical texts, stuff like that, and other people's research. So you just use that again to create something new in your own research. Say for example, there's a data set of the height and weight of people in, say, Mumbai. Now, in Mumbai, this height and weight data, right? The height and weight can be used to find correlation. This height and weight data, it can also be a measure of the health that the people are in. So there are many different categories that the scientists use. So the primary, it is divided into two types, the qualitative and the quantitative. So the qualitative is completely abstract concepts or something that cannot be put a definite mathematical or numerical value to. So what qualitative is if I ask you a question, how do you find India, say for example. So some people may say, oh, I think it's good. But how good? There is no exact mathematical value that someone can put to I find India very good, or I find this thing bad about it. How bad is bad? What is the numerical value associated with the bad that makes like it possible for calculations to be made? So the thing is, qualitative data, it can be transformed by various methods that we'll talk in a later class. But just for now, know that there is qualitative data from surveys and stuff where we ask general open-ended questions and we just note down the answers. The quantitative data is, say, height, weight, the amount of children that a family has. These are all numerical data and can be used as is in a data set. So next we'll talk about the 4 data measurement scales. Now this all is all very basic stuff. I'll go into a little more detailed things in probability in a later class. Like I'll go into the more definite probability, like the different distributions in a later class. So for now, these are all the basics. So there are 4 different data measurement scales in statistics. The first is the nominal. The nominal is just labels. If I assign, say, green, very green, less green to trees, or say I say like I bin the different weights of a class of children. So 0 to 20 is 1 and 20 to 30 is 2, right? But now the nominal one, it is not ordered, so the labels can be in any which order possible. But the ordinal is labels with order. So like 0, 1, 2, 3, 4, suppose they are the labels, then we know that 1 is always after 0, 4 is always after 3. It cannot be in any other order. Now the interval is also similar to the ordinal, in which it has the order, but it also has a definiteness to it and a range of values in between. So say ordinal is only 0, 1, 2, 3, 4. Interval is 0 to 10, 10 to 20, 20 to 30, like that, right? And next we have the most interesting data measurement scale, which is called the ratio. Ratio, you all may know it by another name called percentage. It's like any scale, say for temperature. We have like 0 temperature to 100 temperature and every temperature in between. That is the kind of measurement scale that ratio is. We have a minimum value, a maximum value, and all the values in between. So next we'll talk about frequency tables. Frequency tables are nothing but like different rows of data where we have the number of times it is occurring, that is the frequency, in a table. So we can have only the frequency and the name, or we could make tally marks for it as it is given here. So you can see the different, the one line, one vertical line is given for one frequency, and then the second frequency, like there is 2, right? So 1 and 1. Then if there is 5, what we do is we give 4 like vertical lines and 1 crossed line to denote that it is a bunch of 5. So this is a very like interesting technique which was developed long before any of us were born. So yeah. Then next we have the histogram. In the histogram we have 2 values, one in the x-axis and one in the y-axis, and these can be bins, these can be like discrete values, as it is given here. So 0, 1, 1 to 2, 2 to 3, right? And what we have is we have the frequency. So 0 to 1 is 30 times, like it has the frequency of 30. So we have this whole big block of blue here that is from 0 to 1, and it means 30. Next we have skewness. So skewness is a measure of the amount of the right or the left, right? How much symmetric is your graph? So okay, these lines are made using the points, midpoints of the histograms, and then just connecting these, and so we'll have a kind of curve, and this is the curve that we get, right? So symmetric is where it like increases and then it decreases in a uniform manner. But what if it increases very fast in the beginning, and then it like slowly, gradually goes down, or it can gradually go up and then suddenly like fall in the end, right? So we have right skewed, we have left skewed, and we have symmetric, the three type of skewnesses that we have. Then we have kurtosis. Kurtosis is how flat your curve is. So the most like flattest curve will be platykurtic. The middlemost is mesokurtic. Meso comes from Greek or Latin. And then the final is like very bunched up in the center towards the mean. This line will be the mean somewhere around here. And so this is leptokurtic. Next we have the percentiles. So percentiles is generally like percentage, but what is the maximum and minimum? In percentage we have 0 to 100%, right? But in percentile it can be anything. So say from -4 to 4 we have the percentiles as 50, it comes in between, so 50th percentile, and then we have 60, 70. The 25th percentile is the same as the half of the 50th percentile, like that. Next we come to an interesting topic called correlation. So correlation, often what happens in various scatter data plots, scatter data as in the height versus weight, it can be the age of people in a certain community, it can be anything. So we have an x and y axis, obviously, and then we have the data points. What we try to do is we try to fit a line through the middle of the data points so that either an equal number of points lie on both the sides, right? That is a like common solution. Or what we could do is we take the deviations from that line, like this is the deviation of this point, this is the deviation of this point, right? This is the deviation of this point. So all these deviations we take and we find the mean, and we try to decrease that mean around this line. So the line which gives the mean, like minimum mean deviation, will be the goodness of fit line, which we'll be talking in the next slides. So this is for r equal to 0.7. We see that it is positively correlated. It is like tending to the x equal to y line, which is the 45-degree angle. This is r equal to 0.3, which is kind of more horizontal, and then we have r equal to 0 where it is completely horizontal, right? Then we have r equal to minus 0.7, which is negatively correlated. We have minus 0.3, which is a little less negatively correlated, and then we have r equal to 0 again. So correlation, we'll talk about the correlation coefficient and how we have the derivation, but generally correlation lies between -1 and 1. So next we have the correlation coefficient. The correlation coefficient, I have used the Spearman correlation coefficient. There are many people who use Pearson. There is nothing wrong in using any of those. It's just different situations and different perspectives. So the Spearman correlation coefficient is given by the covariance of the first x, like random variable x, random variable y, and then the variance of each of these multiplied. So we have the formula for covariance as summation of xi minus x bar, right, for x, and then yi minus y bar for y, whole divided by, we do sigma. We know sigma square is the variance, so sigma is the standard deviation, and then we just divide, we multiply these values, we plug in these values, and then we have this r. So based on this r, we see what kind of correlation it is. Either it is negatively skewed, is positively skewed, or maybe it's 0. So this is goodness of fit. This is called the chi-square. This is not x in any way. It's called chi-square, and this is summation over OI minus EI, where OI's are the observations and EI is the means, right? So the EI is the expected count, and we plug in these values again, and the value for x squared will give the kind of goodness of fit. This is what I was talking about when I meant mean deviation, because around that line we find the deviations of each of these points, and the line which like minimizes that deviation is the best fit line, right? Okay, so next we'll talk about hypothesis. So there are two kinds of hypothesis generally, null and alternate. We can have only one null hypothesis, but there may be like more than one alternate hypothesis. I have seen a few places where it has been used, very rarely, but you can check it out. So the null hypothesis is, say we have a problem, right? We want to check how many people are taller than 5 meters. No. Say we want to check how many people are taller than, say, 6 feet. So we'll like the null hypothesis will be that most people are taller than 6 feet with a significance value of 0.5, right? 0.05. Then what happens is we do various calculations, and then we check with a p-value. The p-value is given here. So we check with the p-value. The p-value has a table which we can get off any mathematics book. So either the null value is either the null hypothesis is true or the alternate hypothesis is true. So you can see the significance. This is called statistical significance, which gives the amount of like likely observations and unlikely observations. So we can have that the p-value is very small. Then we can say that we can reject this idea that most people are taller than 6 feet. If it is big, then we can say that most people are smaller than 6 feet, right? So okay, next we have probability distributions. I thought I wouldn't talk about probability distributions in this slide, but maybe I'll like. So hey, next we'll talk about probability distributions. These are the discrete distributions. I'll talk about the continuous distributions in the next class. So be sure to check this channel out and like and subscribe. So first we have the binomial distribution. Okay, first we have the binomial distribution. It is generally denoted by B. In bracket we have n and p, where n is the number of observations and p is the probability of success. So we have n, the number of observation. What do you mean by that? Say we are throwing a dice. So how many times do we throw that dice? That gives the value n. And if the dice has like 6 faces and it is a non-biased die, so we have 1 by 6 in each of the faces as the success. So p is probability of success, which is 1 by 6. So the probability mass function, which is for discrete distributions. The probability density function will be for continuous distributions, as I'll be talking later. So the probability mass function is denoted by either fx or px equal to x, right? So fx equal to ncx. This is the combination of n and k. So this term, it is generally n factorial divided by k factorial into n minus k factorial. Then we have p to the power k, where p is the probability of success, and q to the power n minus k. Q equal to 1 minus p, which is the probability of failure, right? Probability of success and probability of failure will always add up to 1. So the conditions under which the binomial distribution holds is that the n different experiments should be independent. Then we have the P is the probability of success, and K is the number of successes that we want. Next, we have the Poisson distribution. So in the Poisson distribution, we have only one parameter, that is lambda. But in this lambda, we have hidden two parameters, n and p, just like binomial. What makes it different from binomial is that n, the number of trials that we have, it tends to infinity. And the probability of success, it is very minimal. It is almost zero, say 0.01 or 0.02, right? So n and p, if we multiply these two, we'll get lambda. And so lambda is kind of the mean also of the Poisson distribution, as we'll find out. And so in the Poisson distribution, we have E, which is called the Euler's constant, as you know, is equal to 2.7183. And then this is the formula for the PMF, the probability mass function of Poisson distribution. If you want, you can comment down below if you want the derivation of binomial to Poisson. I have it in a pretty easy way, but you'll find the same on the internet and in a variety of books. I will mention a couple of books that I have used myself. For studying this. So yeah, maybe it will help you out. So yeah, the Poisson distribution is mostly for events that have almost no chance of happening, but that is in a long period of time. So the number of meteorites greater than 1 meter diameter that strike Earth in 1 year, right? So this kind of event, it happens all the time, but the exact event, the probability of success is almost zero. The number of patients arriving in an emergency room between 10 and 11 p.m. The number of laser photons hitting a detector in a particular time interval. You can check more examples of the Poisson distribution on the internet and see as we decrease the lambda, we have a curve like this. It slowly tends to a symmetric distribution. Next, we have the hypergeometric, which, if you ask me personally, I think it is a very redundant distribution, but many people tend to use this name for this kind of distribution. So the hypergeometric is nothing but it is the hypergeometric distribution, it is just combinations. So if you have an urn of red balls and black balls, what is the probability that if you take 5 out, then you will have 3 black and 2 red, right? That is the kind of distribution that we are talking about, and that is given by hypergeometric distribution. Anyone who is fluent with combinations need not remember this hypergeometric distribution at all. So next we have the negative binomial distribution, which is denoted by NB, and it is kind of an important distribution. We have the parameters as R and P. This is the same as the binomial distribution, hence the name, but it is kind of different in the sense that one particular part that is similar with the binomial distribution, one particular part which is similar with the binomial distribution, it has a negative minus sign to it, right? So that is the only reason that this is called the negative binomial. And so this is kind of you can see one example here, the length of stay at an hospital. There is a very interesting problem that I want to talk about in negative binomial distribution. I'll just give you the problem, and if you have if you cannot find if you cannot find the answer on the internet, then tell me in the comment section below and I'll be happy to give you the answer, right? So the problem I want to discuss is Banach matchbox problem, and I think I studied this in Anderson. So the Banach matchbox problem is basically this. There is a professor, right? And what he does is he's bored, he's waiting for someone. So he has 2 matchboxes in each of his 2 pockets. What he does is he tosses a coin, right? What he does is randomly, it is random, that is the probability of success is half, he takes out like the matchbox from one of his pockets, so it is already halved. Then from that pocket that he from the pocket that he selected, he takes out the matchbox, and then he takes out one match from it, lights it, and throws it away, right? And he does this many times, say r or n number of times. What is the probability that when r successes, what is the probability that after a certain amount of trials, say k trials, that when he takes out one matchbox and he takes out one match, then the matchbox becomes empty? So you get the problem, right? We have a professor who is waiting for someone. He's bored, so he has two matchboxes in his pockets. He does not smoke, mind you. Don't smoke, it's bad for your health. So he has two matchboxes, and what he does is he takes one out randomly, he lights the match, and he throws it, right? What is the probability that after k trials he will have a matchbox which is completely empty if he takes out one match? So that is the matchbox problem. It can be made in various different kinds of ways. There is another problem that is similar to the matchbox problem, which is where this guy, he is waiting for his girlfriend, and what he does is he is just bored. He takes 2 steps front, and he takes 3 steps front, 2 steps back, something like that, and then he turns a few times. Say he goes from south to east, east to west to north, and then what is the probability that he is say 50 meters from his starting point? So these kind of interesting problems can be found in the negative binomial distribution. I suggest you take a look at some of the examples on the internet and on the books. Books basically, the most interesting one is, I think, Anderson. I think you should take a look at Anderson. Also this other guy, check out. So now we'll finish off by talking of moments and the moment generating function. So what is the moment generating function is basically we have the f, right, the probability mass function. So what we do, in place of this x, we put tx, right? Say the variable has undergone a certain transformation, say it has been scaled from x to tx, then what is the difference in the expectation? So that is given by the moment generating function, and it is e of tx, and whatever the value comes, it usually comes in summation for the discrete distributions. So this moment generating function is basically a summation value of a function of tx, and then over x we have the summation, so we break the summation in binomial form, and then we ignore the higher order terms. So that is how you get the basic formula of moment generating function. And the coefficients of t square, t cube, they are denoted by u1, mu1, mu2, mu3 based on the Greek alphabet. And mu1 is always the mean of a distribution. Next we have quartiles. Quartiles are also similar to the mean median. So we have q1 as the mean of the distribution, then q2 is the half of the minimum of the distribution, the mean of the distribution, and q3 will be the minimum of mean of the distribution and maximum of the distribution, and then we have we basically half it every time, and so those are the quartiles. So yeah, that's enough for today's class. I think it's already 10 minutes, and I would like to thank you for joining me in this class. And if you want to further ask me any questions, then you can directly email me. My email is given below. And yeah, subscribe to Analytics Boom, like and subscribe the channel, share it with your friends so that they can come on this journey with you, and adios.